So earlier in the semester, we used tangent lines to introduce the derivative. Now what we're going to use is areas to introduce the definite integral. And then in section 5.3, we'll be introduced to the fundamental theorem of calculus, which shows a connection between these two. So to start off, we'll start off with some easy ones where we don't need calculus. So if you look at this problem here, it says find the area under the curve between x equals 1 and x equals 4. And here's the curve y equals 2. So no calculus required here. Between x equals 1 and x equals 4. Well, I mean, we could break this up into pieces, and it makes it really easy to see. The area is going to be 6. Or we could use this formula from geometry, length times width. Get this length, which is 3 units, the width, which is 2 units, and we get 2 times 3 equals 6 square units. So pretty easy, no calculus needed for that one. And the next one, not quite as easy, but still not too bad. If you want to find the area under this curve between x equals 0 and x equals 2. So it looks like we've got something like this. Well, this area we can also find with a formula from geometry because we just got a triangle there. And we know the area of a triangle is 1/2 base times height. Or in this case, 1/2, the base is 2, right? The base along here is 2, and the height is going to be 4. So the height coming up here is 4. So we end up with 4 square units. Then we come up with this other one. Find the area under this curve between x equals 0 and x equals 5. So between x equals 0 and x equals 5, so we want to find this area here. Well, at this point, you know, we've got this kind of strange curve here, and we definitely don't have any formulas from geometry to help us out here. So if we wanted to figure out the area here, we're going to need some help with this one. So to do this, let's think back to when we first started talking about derivatives. And we first approximated the slopes of tangent lines using the slopes of secant lines. Then we took the limit of the slopes. Remember, we took the limit of the slopes of these secant lines to find the slope of the tangent line. So we were using limits here. So now what we're going to do is we're going to approximate the area of a region using the areas of rectangles. We will then take the limit, so here's a limit again, limit of the areas of these rectangles as the number of rectangles approaches infinity. This will allow us to find the exact area of the region. And we're going to do something that's very similar to what Archimedes did a long time ago. So he was a Greek mathematician and typically regarded as the best mathematician of antiquity, and always on the list of the top 4 or 5 mathematicians that the earth has produced. He's always on there. And he understood the basics of integral calculus. And he used what's called the method of exhaustion, which is pretty much what we're going to do, but we extend it a little bit further by taking the limit. And the limit is something that the Greeks, they never used the concept of a limit. They had a really hard time with infinities. And actually the concept of nothing also, but infinity gave the Greeks a hard time. And some of you may have heard of Zeno's paradoxes, which mathematicians have considered Zeno's paradoxes settled. They don't consider them paradoxes anymore because they argue that they're settled using the concept of a limit. But not everyone agrees that it's settled, and especially in philosophy and maybe even in physics. There's some debate as to whether those are truly settled or not. But I'll just mention one of them because these paradoxes have a lot to do with calculus because of the idea of a limit. So one of the Zeno's paradoxes is the idea of if you have a person standing here, here's this person, and let's say it's some guy and he wants to go to this wall right here. So the idea is Zeno would argue that he'll never get to the wall because before he gets to the wall, he's going to go halfway there. So he'll be right here. And then before he gets to the wall, he's going to go halfway there. So then he'll be right here. And then he'll go halfway, and he'll continue going halfway, so he'll never actually get there. And of course, we know that he does get to the wall. So Zeno would say, well, what's wrong with my argument? How can he get to the wall when we know he can always just get halfway and then halfway and halfway and halfway? So we can see kind of a geometric idea of this if you think of distance. So if you think of this instead of like, okay, what is the total amount? So this person's going to go halfway to the wall, and then half of that, and then half of that, and then half of that. So this is kind of like a geometric interpretation. And if we keep adding this up, can we go to infinity? Can we go past 10? I mean, what does this add up to? We're going to keep going an infinite number of numbers. An infinite number of numbers are going to be added together. So couldn't it go as high as we want? Well, it's, may seem a little strange, but the answer is 1. And you can see the answer if we think of a square that is 1 unit by 1 unit. So let's say this is 1 unit by 1 unit. And you can see these numbers inside here. If we think of the area of the square is 1 by 1, which is 1 square unit. So here's 1/2. Right, that's this one. Now take half of what's left. That's a total of 1/4. I'm going to add that together. Then take half of what's left. That's going to be 1/8. And I'm going to add that together. You can see we can keep going, but we know what we're going to get. When we add all of these up, we're going to get the entire area of the square, which is 1. So this, actually, all of this just adds up to 1. So this is a paradox. I didn't probably say this paradox exactly right, but it's very similar to that. And if you get a chance, just look up Zeno's paradoxes. There's a handful of them, but all of them essentially come down to this concept of completing an infinite number of tasks in a finite time, or something along those lines, where the concept of a limit, as far as mathematicians are concerned, can answer those questions. So to see what we're going to be doing in section 5.1, let's take a look at an example here. So we've got example 1 says, use rectangles to estimate the area under the parabola y equals x squared from 0 to 1. So we've all seen this parabola a whole bunch of times. So let's say this is 1 here and 1 here. So y equals x squared goes something like this. So here is, let's say, y equals x squared. We want to find the area underneath this curve between 0 and 1. So we are looking for this area right here. So what we could do is start off with an approximation using a triangle. So we know that the area underneath this black line here, the area under that black line could be found by the area of a triangle, which is 1/2 base times height, right? Which is going to be 1/2 base times height, which is just 1/2. And we can see that our area is definitely less than that. So far, we have a real rough approximation. We can say our area is less than 1/2 square unit, right? So we start off and we have got this. We know our area is bigger than 0. There is something here, but it's less than 1/2. So here's where we're going to start getting into this idea of integration. So we're going to try to do better. We're going to try to get an approximation of the area using 4 rectangles and right endpoints. So first, let's redraw our parabola. Goes something like this. And so we want to find this area right here, right? We're looking for this area. So what we're going to do is we are going to break this up into 4 rectangles. And they're going to be, we'll break up the number line. So we'll use, there's 1/2, 1/4, 3/4, and then 1. And it says using 4 rectangles and right endpoints. So what that means is we're going to think of this as coming straight up here. So for this first rectangle, here's the left endpoint, here's the right endpoint. We're going to use a right endpoint and just bring this straight across. So for the second rectangle, here's a left endpoint, here's a right endpoint. We use a right endpoint. And the right endpoint we're basically just using to get the height of our rectangle. And if we continue along this way, we will go like this. Now we're going to find the area underneath these 4 rectangles instead of the area underneath the curve. And we know we're going to be too high, right? We're going to overestimate this because we have this area up here that's too much. It's above the curve. But it gives us a starting point. So the way we do this, the notation for this is R sub 4. And what this means is we're using right endpoints, 4 rectangles. Right endpoints and 4 rectangles. And then the area is going to be the area of this first rectangle plus the area of the second rectangle plus the area of the third and the area of the fourth. And we know the area of a rectangle is just base times height. And isn't it true that the base of each of these are going to be 1/4? This distance is 1/4 in each case. So we could go, okay, this first rectangle, base times height. Okay, there's the base, 1/4. Now the height, remember that this curve is y equals x squared. So the y coordinate right here is just 1/4 squared. The y coordinate right here to get that height is 1/2 squared, right? So to get each of these y coordinates, we just have to plug in x into the equation y equals x squared. So this first one is going to be base 1/4 times height, which is going to be 1/4 squared because I plug in 1/4 here to get what the height y is. So base times height, which is 1/4 squared, plus, now I come over to this rectangle here, base is 1/4. So I got 1/4 base times height. Well, the height of this rectangle is whatever the y coordinate is here. And the y coordinate here is x squared, so it's 1/2 squared. So multiply by 1/2 squared. And then the same thing here, base is 1/4. The height of this rectangle, the third rectangle, is just 3/4 squared, right? You plug it in there. So you get times, or plus 1/4 times 3/4 squared. Then finally go to the last rectangle, base is 1/4, and the height is just going to be 1 squared, which is just 1. So we go plus 1/4 times 1 squared. So if you go through and do all the calculations, you get 0.46875. And a little bit of a warning here, 5.1 and 5.2 are fairly tedious sections. We do a lot of stuff like this. But here's what we need to know. This is too big. We know it's too big because we've got all these extra areas up here, right? All this red here, that's extra area that we don't need. So all of this red area is an overestimate. So one thing we can notice is this. With an increasing function, like y equals x squared, it's increasing, meaning as we move along here, as x goes up, y goes up. It's increasing as we go. With an increasing function, r sub n will be too big. All right, because r sub n for each of these rectangles is taking the tallest point, and it's always going to be taller than the first point because the function's increasing. Okay, so r sub 4 gives us we're a little bit better than we were. It's better than using the one triangle, which gave us an area of 0.5, so we're narrowing it down a little. But now let's try the same thing with 4 rectangles, but using the left endpoints. Okay, so we'll use the left endpoints this time. So do the same thing. Let's do, this will be 1 and 1. And draw our graph of y equals x squared. So it goes something like this. So then we can do the same thing as before. Let's break this up into 4 pieces. So we have 1/4, 1/2, 3/4. And we've come up here. Well, this time we're going to use left endpoints. We can still do this though. We can come up here. But this time, when you look at this first rectangle here, the left end point is 0. So this first one is going to be going to have no area at all. Then you come to the second rectangle. Here's the left end point and the right end point. We want the left end point this time. So we come across here. And then, well, again, let me shade in what we want. We want all this, right? We want the blue. We want to find the area under the curve. So we come to the third rectangle, and again, we're going to use the left end point. So that means we will use this number to find the height, and then finally the left end point on the last one gets us here. So we're going to, instead of finding the area under the blue, we're going to find the area under the black here. We can see by looking, we're going to be under the estimate now because we're going to have all this area that we're not counting. But if we go through the same process and we find L sub 4, and the notation is similar, left end points, 4 rectangles. So we're going to find the area of this first one. Well, this first one, base is still 1/4, right? The base is each going to be 1/4, but the height now, so look what we're doing now. Now we're actually using this end point, and when we calculate this, we're not going to use this one. So it's sort of like we shifted everything over. So if you look at our last one, last time we used these numbers here, and we didn't use 0. We didn't use 0. So it's kind of like the numbers that we're going to use, we're shifting them all over this way so that we're not going to use the 1, but we're going to use the 0. And that's what happens to the left end point. So L sub 4 is going to be base 1/4 times height, which is going to be 0 squared, because that's the height of this first rectangle. This rectangle, this first one has an area of 0, because the height right here is 0. Then we're going to add this rectangle in, base 1/4. The height is going to be 1/4 squared. So going to go plus, oops, this is supposed to be 1/4 here, right? Base times height. So then the second one is 1/4, and the height is going to be 1/4 squared. So that's this one, base. The height of this rectangle is 1/4 squared, right? Because again, this line is y equals x squared. So if we want to find any of these points, like this point, or this point, it's just going to be the y coordinate at this point. So it's going to be 1/4 squared for this one. Now this third rectangle, we're using the left end point, so the third one is going to be 1/2 squared. So base is 1/4 times height 1/2 squared. So go plus 1/4 times 1/2 squared. Then finally go to this last rectangle, and the base again is 1/4, and the height is going to be 3/4 squared. So go plus 1/4 times 3/4 squared. If you go through that math, we'll get 0.21875. And we know for sure it's going to be too small, because it's missing all of this red here, right? It needed to count that to get an estimate, and it didn't. It's missing all of that, and we can say in this case with an increasing function again, because we've got an increasing function, with an increasing function, L sub n underestimates the area. Or to be consistent with the one above, I guess I should have said L sub n will be too big. But you get the idea, right? Because it's always gonna pick the shorter side, so it's gonna be too small. But we do have some improvement now. So we can improve on our estimate for the area. The area underneath y equals x squared between 0 and 1. Now we can say this. It's between this number and this number. So if we did the same process but used 8 rectangles, and you can imagine, I'm just going to draw 8 above so you can see what's going to happen. But the more rectangles we have, if you look up here, let's say instead we use 8 rectangles. So if we used 8 here, we'd be coming up here, 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 and here. And now if we use the right endpoints, we're going to get here and here. You can see what's going to happen. We're going to get a lot less errors, right? And here and here. So we've cleaned up a lot. We've got all this stuff here that used to be an error will no longer be an error. So when we divide these into more rectangles, we're going to get a better approximation. Now the trade-off, as you can imagine, is we're going to get more calculations. It's not as big of a trade-off anymore in modern times with calculators and computers, but it used to be. So with 8 rectangles, we're doing a little bit better yet. We can do better than this. With 8 rectangles, we can divide it. We can see that we have a little bit more precision here. And then further divisions give us this. So when n is 10, 50, 100, or 1,000, we get these. And what we want to do is see if we can notice, does it look like these are approaching anything? Like, does it look like maybe there's a limit, like a limiting value here, like infinity here. Of course, we can't really break this up into an infinite number of pieces, right? We just can't do it. We can't break it up into an infinite number of rectangles and then add up the areas of all those rectangles, but we want to see this is like the limiting value. As n approaches infinity, what does it look like L sub n and R sub n are approaching? So if you just had to guess, we just had to guess a number here, I think most of you would probably say 1/3. It looks like it's approaching 1/3. And we're going to see that actually is true. We're going to see later, not very much later, pretty soon actually, but it can be shown that the area equals exactly, notice that's not an approximation, that's exactly the limiting value of L sub n as n approaches infinity, and also equals exactly the limiting value of R sub n as n approaches infinity. Remember, n is a number of rectangles. So if we had an infinite number of rectangles, they'd be infinitely skinny also, right? But the limiting values of this is exactly 1/3. So now that you see a little bit about what we're going to be working on, let's see if we can generalize this process and figure out what integration actually is. So if we want to find the area under this curve, we're going to divide it up into a bunch of rectangles. So let's say we want to find the area under this curve, y equals f of x, between the point A and B, just some x values. So what we do is we divide it up into pieces, and we're gonna call this first part right here, we're gonna call this x sub 0. So A is x sub 0, and B we're gonna call that x sub n. So then this first little spot here is going to be x sub 1, and that will be x sub 2, x sub 3, x sub 4. Then over here we'll have this one would be x sub n minus 1. And that's about as far as we need to go. So for this one, we're going to use the right endpoints. So for this first rectangle here, this first one, we're not going to use the left endpoint, we use the right endpoint. So we'll follow this up, and where that hits, we come across. Same thing with this one, right endpoint, we come across, so that we will have something like this. So some will be overestimates, some will be underestimates. And over here, so we are going to find the areas under these rectangles. And the general idea is the more rectangles we have, the better we'll be. But then there's more calculations also. So, all right, we've got this picture. So let's see what we've got. So the width of the interval, well, the width of the interval, meaning this interval from A to B. So in other words, let's say B is 11 and A is 1. The width would be 11 minus 1, or 10, right? So the width is just going to be B minus A. Width of the interval is just B minus A. And then we're going to have this little delta x here. This is just going to be the change in x. That's going to be the width of each rectangle is going to be delta x. And what that's really going to be is the width of this, which is B minus A, divided by how many of these rectangles there are, right? So this delta x really is just going to be B minus A over n. Then also we can see that looking at what we've got here, we start with x sub 0, and x sub 1 is just going to be A plus delta x. So x sub 1 is going to be A, our starting point, plus delta x. Right, and x sub 2, that's just going to be A, right, A plus 2 of these delta x's, because each of these is going to have the same width of delta x. So that x sub 2 is going to be a plus 2 delta x. And of course, x sub 3 would just be a plus 3 delta x and so forth. And then for this part here, we're using the right endpoint, right? So for us, we're using the right endpoint. And we can approximate the area of the ith rectangle by thinking of it like this. So here is the x-axis. Here is y equals x squared. Then what we would get is the two sides of the rectangle here. So if this is the ith rectangle, then this would be x sub I, and then this would be x sub I minus 1. Right? Like just think if it's the second rectangle, here's 1, 2, here's the second rectangle, this is x sub 2, and this is x sub 2 minus 1. So this will be here. So since we're using the right endpoint, this would come across here. And to find this area right here, this area under the curve, we would have this would be the height, which is going to be f of x sub I, and the width is going to be delta x. So just looking at that picture, we can see that the area of the ith rectangle is going to be f of x sub I times delta x. So for any one of these rectangles, the area is just going to be width times height, right? Just like a rectangle. So the width is going to be the change in x delta x. The height is going to be the function's value at this input. So with that in mind, we can find an approximation for the area under the curve. So the area under the curve can be approximated by r sub n. So remember what this means. We're using the right endpoint and we're using n rectangles. So think about what that means. That means we would have f of x sub 1 times delta x. Just to make sure we're clear with that, let's look back at the picture here. We're using the right endpoint, f of x sub 1, that's going to give us this height, right, times delta x. So we start here, so we don't start at x sub 0. We will start here, though, when we're using the left endpoint, but when we're using the right endpoint, we start at f of x sub 1. Okay, and then with the right endpoint, we'll go all the way to x sub n. When you do the left-hand point, everything gets shifted over 1. So we would start at x sub 0, and we would go to x sub n minus 1, because for the left-hand point, we're going to use this. We're going to use this to find the height of this rectangle. So for the left-hand point would be up here. Okay, so going back over to here, r sub n, if you look at the picture, and then you can see that we're basically just going to add up all these rectangles all the way across. So we'll get f of x sub 2 times delta x plus, and we would keep on going, and we would get f of x sub n times delta x. And then with a little bit of algebra, we could factor out that delta x, and that's going to basically be delta x times f of x sub 1 plus f of x sub 2 plus all the way to f of x sub n. And if you think about it, what these are all y coordinates, right? These are just the y coordinates. The function, when you plug in x sub 1, gives you the y coordinate at x sub 1 and the y coordinate at x sub 2. So we can basically add up all the y coordinates and multiply that sum by the change in x. And what else do we have here? Well, as n increases, the area approximations get better and better, which we've seen, right? The more rectangles we have, the better the area is, the smaller the errors are. And we approach the exact area as a limit. So here's this idea of a limit. So to get the exact area, we actually need that limit. We're always going to have approximations until we take the limit. And it was just like before when we were talking about derivatives. We were taking the limits of those secant lines, but we would use the slope formula from algebra class, so we would get an approximation until we actually took the limit, and then we got the slope of the tangent line. So very similar here. So if you want to get the exact area, not an approximation, then we're going to have to take the limit. If you want exact, we need the limit. And you can see it here. So the area equals, not approximate, but equals, the area equals the limit as n approaches infinity of r sub n. And that's the limit of this. So the one above, we didn't take the limit, we just added these up. But now n is going towards infinity. So if n is not a finite number, but a limit as n approaches infinity, we're taking the limit of the sums of all of these. And then we can do that with the left-hand limit also. So if we're going to take the limit, it doesn't matter if we're using right endpoints or left endpoints. For an approximation, it will. If we're doing an approximation, we're not taking the limit, we get different numbers for these, as we saw in the very first example. But when you're going to get the exact area by taking the limit, it doesn't matter. These are going to be exactly the same. And in fact, it doesn't have to be the right endpoint or the left endpoint. It could be any point. So sometimes you see this phrase, sample points, x sub I star. This just means it could be any point at all. Using any point for the height. It could be the midpoint, a random point in that little subinterval. They're just sample points, but still we get exactly the same. So if there's a limit involved, it doesn't matter where you get the height, you're going to get exactly the area. So this one, just to fill in the blanks over here, this is using right endpoints. Using right endpoints, using left endpoints. And then this just means using any point in the subinterval, or in each subinterval. Sometimes they'll refer to this here as right sums. So if you hear right sums, they're referring to using the right endpoints. So left endpoints, of course, that'd be referred to sometimes as using left sums. And then when you use sigma notation, we can rewrite all of those three things above a little simpler, because if you look at what we've got here and think about how this is, n goes 1, 2, 3, 4, all the way to n. Well, summation notation allows us to do the same thing. So let's come down here a second and review summation notation just real quick. So we'll do a quick review. So review. If you have something like, so this is the Greek letter sigma, the capital sigma. In statistics, you'll see small sigma, which looks like this, but this is the Greek letter sigma, and with something like this. And this always means, whenever you see this sigma, it means sum. It's kind of like this discrete analog of integration. We're going to sum these things up, but they clunk along by integer inputs. So this index I starts at 1 and it goes to 5, and all we do is do whatever this thing says, and we always add. When you see sigma like this, think sum. So we start with 1. What this means, I put a 1. I put a 1 in here, and then I add. And now this index goes to 2. I put the 2 there and add. And now the index goes to 3, and it keeps going until it gets to the 5. So this is basically going to be 3 plus 4 plus 5. So we get 9, 10, 11, 12, 13, 14, we get 15. So one that's a little more complicated, if we had something like I equals 1 to 3, of I squared minus 1. The way this would work, we start with 1. We plug this in here. That's going to be 1 minus 1. So it'll be like 1 squared minus 1. And then plus, right? We always add. That's a 1 right there. 1 squared minus 1 plus. Then the index goes to 2. So we plug a 2 in here. 2 squared minus 1. So you go plus 2 squared minus 1 and then plus, because it's always plus. We plug a 3 in there, then we're done. It goes from 1 to 3 and it stops at 3. So we plug a 3 in there. Get 3 squared minus 1. So that would be 1 minus 1 plus 4 minus 1 plus 9 minus 1, and you could add it up. So basically, I just wanted to review, but that is in Appendix E in the book. So if you're a little rusty with summation notation, it's in Appendix E. We don't really have to be, we're not going to use it too much. Just we're going to use it right here. Just make sure that we understand what this means. But you'll see it a little bit more in Calc 2. So right here, we could rewrite the above, because isn't this really saying sum of this? So starting at 1, so you get f of x sub 1 times delta x plus, then this goes to 2, f of x sub 2 delta x plus, and it goes to 3, and you go all the way to n. So that is exactly what we did above. This is the right endpoints. Right, that's the area using right endpoints, and this is using left endpoints. And you can see when you use left endpoints, all you do is you're going to start at f of x, and I plug a 1 in there, you get x of 0, right? So we're going to start at 0. And when we plug an n in here, at the end, our last one will be n minus 1. So we don't use the right endpoint in that last rectangle. We're going to use the left endpoint. And then this, again, is just using any points. So these 3 things right here are just the previous 3 things written in more compact form. So we're going to see that we can interpret the area under the curve as a distance traveled. We've got this example here. So in the 8th edition of the book, it was on page 377, number 18. But in the 9th edition, it's page 382, number 14. But before we do this one, I want to do an easier example that will lead us into this one. All right, so let's take a look at this easier example before we do the one from the book. And you can see that we've got a vertical axis here, which gives us the rate in miles per hour, or what we could think of the velocity. And then the horizontal axis gives us the time. And we've got this car, and let's say that it is just driving 60 miles per hour for 3 hours. So if we wanted to know the distance it was traveling, we've got a formula from way back when in geometry. Distance equals rate times time. And also, if you notice that this area, if we wanted to find the area of this rectangle, it would be this times this, right? So this is going to be 60 times 3. So the area in this case would be 60 miles per hour, right? That's this dimension here. So area of a rectangle, of course, is length times width or base times height, however you want to say it. But basically, it's going to be this times this. So 60 miles per hour times 3 hours. So multiply that times 3 hours, which then we could just put this over 1. And when we multiply here, we can see that the units are going to cancel. The units of time will cancel, so hours are gone. And the only units that are left is miles. So when you multiply straight across, we end up with 180 miles. So the area of this rectangle could be interpreted as distance equals rate times time, because it's really what this is, rate times time. So this area gave us a distance. So these areas under the curve can be interpreted many ways, because they're basically going to have, there'll be some variable here or some measurement here and another one here. So the area could always be just this times this, right? And this is a real easy case because it's a rectangle. We know a formula for this from geometry. But this example 2 in the book is going to be the same idea. If you keep in mind what we just did, it's the same idea. It's just not as easy to calculate because it's not just a rectangle. All right, so now we've got a picture here. Let's take a look at this problem. And this one, it says the velocity graph of a car accelerating from rest to a speed of 120 kilometers per hour over a period of 30 seconds is shown. Estimate the distance traveled during this period. Well, just like before, we've got the rate here and the time here, right? So we know distance equals rate times time. So we still have this distance equals rate times time. So that's the same as before. Last time, though, we had an easy way to find this because we had a rectangle. And we know the formula for a rectangle, so we could find the area under the curve pretty easily. But now we need to find this area under the curve, and we don't have a formula. So what we could do, kind of like what we always do, what we have been doing in calculus, is we could break this up into a bunch of pieces. So let's go ahead and break this up into these, into some pieces that we could make into rectangular pieces. So I'm just going to break this up into 6 pieces, just because it works out nicely to use 6. We can break them up in these 5-second increments. Okay, but I want to try something different this time. So what we've done so far is we've used left endpoints. So like if we wanted to find the area of this rectangle right here between 5 and 10 seconds, we'd use the left endpoint and come up here and then cut over and use this rectangle. Or we've also looked at the right endpoints where on this same rectangle we'd come up here and use this for the height of the rectangle and cut over here, and we have this rectangle up here. But what I want to do this time is use the midpoints. And it's another technique that we use sometimes. So to find the midpoint, or to find the height of this rectangle with the midpoint, we take this point right in the middle and we go up here and then cut across here. And the midpoint has an advantage of, like if you just draw this one, if I use the midpoint here to get the height of this rectangle, I come across here, it has kind of an advantage where it misses this area here, but then it overestimates here, so they sort of cancel out a little. So I want to use the midpoint for this one. So we're going to use these midpoints here. So actually this would be, we use this right here. This first one, this would be 2.5. This will be 7.5, 12.5, 17.5, 22.5, 27.5. And we'll use those midpoints to get our rectangles that we're going to use. So this will come up here. Oops, and kind of cut over like this. Come up here. And we're going to use the midpoints this time to get the heights for our rectangles, and we'll use the areas of these rectangles to approximate the area under the curve. Okay, so then we've just got to calculate these areas, and we use that as an approximation for the area under the curve, which in turn is the approximation for the distance traveled, right? For this car in this 30 seconds to see how far this car traveled. All right, so what we've got this car that started. This is the velocity curve here, right? This is our velocity curve. Started at rest, and 30 seconds later is going 120 kilometers per hour. So this velocity curve, we're going to approximate the area under the velocity curve by using these rectangles. So what we've done in the past is we've found the width of the rectangle by going delta x equals b minus a over n. Now this time we don't have x here. Our independent variable would be t, but same idea. So we can say delta t equals b minus a over n, which in this case we would have 30 minus 0 over 6, because there's 6 rectangles, right? 1, 2, 3, 4, 5, 6. So this is going to give us 5, and then this is the change in t, right? The change in time. So this is 30 seconds minus 0 seconds. We divide it into 6 pieces, so we end up getting 5 seconds. So our width here of each of these rectangles is 5 seconds. Now we've already got an issue going here because this time is in seconds, this time is in hours. So let's just clean this up. Let's just change seconds into hours, just so we can talk about when we multiply these together, we have to have the same unit. So let's just change seconds into hours so we can do that. So 5 seconds, if we take 5 seconds, and then if we realize that in 1 hour is 60 minutes, and in 1 minute is 60 seconds, that means in 1 hour we have 3,600 seconds, right? And so if we multiply these two together, whoops, let me put the units in here, 3,600 seconds. The seconds will cancel. We're going to be left with hours, and we'll get 5 over 3,600, which will give us, this will be equal to 1 over 720, that many hours. So each of these gaps, which is 5 seconds, is also 1/720th of an hour. Okay, so we use that, and then when we multiply this times this, the units will cancel because it's kilometers per hour times hours, which will leave us just kilometers, the distance, right? That gives us the distance. So the way this works then, if we're going to calculate m sub 6, what we're going to get is basically we just have to find the areas of these 6 rectangles, right? So this is going to be, this first one, the base is delta t, right? So the base is going to be delta t times the velocity at 2.5 seconds. That'd be this first one. And then we have to add the second one. So the second one is going to be plus delta t. So we just calculated delta t over here, right? But just the general idea is going to be the change in t, which is the base, and then times the height at 7.5 seconds, because you want the height. So you want this value of this velocity curve at 7.5 seconds. So times velocity at 7.5 plus delta t times the velocity at 12.5. We go right down the line here. Delta t times the velocity at 17.5. Delta t times the velocity at 22.5. Plus delta t times the velocity at 27.5. Okay, and then of course we could factor out delta t. But just to save a step, I'm going to, instead of writing delta t, I'm going to write it as this, right? It's 1/720th. So I'm going to factor out delta t, or 1/720th. And then we'll just have the velocity at each of these midpoints that we need to calculate. It's a little bit tedious, right? Okay, so we get this, and then I'm just going to fill in the numbers here that I came up with. So we could get different answers, because remember, how are we going to get these? We don't have a formula to plug into. We're just going to eyeball the curve, right? So when I look at it, velocity at 2.5 looks like the velocity at 2 seconds is about 32 kilometers per hour. But I'm eyeballing it. And these are the numbers that I came up with. Yours may be a little bit different. Whoops, that's 103. Plus 113 plus 119. All right, so that's what I got. Maybe something different, as long as it's fairly close. We're probably just fine. And if I add up all those numbers in the parentheses, I get 520 over 720, which ends up giving us roughly, let's see, that gives us roughly 0.72 kilometers, right? The units are kilometers, because each one of these is the unit of time times unit of velocity. Time is in hours, velocity is in kilometers per hour, so the hours cancel, so we just get 0.72 kilometers. So the area under this curve, it's actually an area, but it represents the distance traveled, right? It's an approximation for the distance this car traveled. All right, so hopefully that one makes sense. And then it brings us to a program on the TI-8384. And this program's just, it's kind of nice to have for this section. And in the homework, it asks you to use a program on number 27 and 28. And it's, I think it might say the right endpoint, but it doesn't matter. We can use a left endpoint. But I just wanted you to have a program to see basically what we're doing in a little quicker than doing it by hand. And this program, this is from the TI-83 and 84 have a basic language interpreter. And basic language used to be a language everybody would learn initially. But now it's, it's one of those ancient languages that's probably on its way out. Somebody when they were in college learned all these extinct languages like COBOL and Fortran and Pascal and things that I really never heard of too much anymore. But BASIC was the first one that was typically taught, and it's just super easy to learn, and it's in the TI-83s and 84s. Now the newer calculators I think are using Python, which is probably a good idea since that's the one that is definitely more popular than the BASIC language. But I'm just going to walk you through this, and you can see that basically what we did right there is all right here. So just to give you the basic idea, so this S, this is going to be the sum when we're adding all these rectangles together. So just you can see what we just did when we do the left sum or the right sum or the midpoint. They're all basically the same idea. This one is the left sum. But basically we start off with the calculator. We're gonna store 0 in S. So S is like is the sum of all of the heights of the rectangles. And you can see what it's going to do. It's going to ask us for the minimum. So like in the problem that we did initially, we're finding the area of that, the area underneath that parabola, y equals x squared, from 0 to 1. So if we were going to do this on the calculator, we'd say the minimum is 0, the maximum is 1, n is the number of rectangles we want. And then look at this. This is just delta x, right? B minus a over n stores in d, so d would be like delta x. Then we've got this little for loop, and basically it's going to start, the way the for loop works is going to start at, it says basically for I equals 1 to n. N being the number of rectangles we've got, it's going to take this sum, and then all it's going to do is add up the height of the next rectangle, because it starts at A, our initial value, plugs it into Y. So in this case, if we were going to use this on that parabola y equals x squared, and y1 we would put x squared. And then so it's going to just plug this into y1 to get the height of the new rectangle, and then it's going to store that in S. So it's going to keep adding these together. Then it's going to advance to the next rectangle. We're going to add delta x to our starting point. And then the for loop will keep doing this until we get to n, then it will stop. We get to the n that we want, it will stop, and it's going to display d times s. Well, d is delta x, and s is the sum of all the heights of the rectangles. So basically, when you multiply this together, you're going to get the same thing that we got, which is the approximation for the area under the curve. Okay, so I think I'll probably just make a video where I walk through this, just in case if you want to have this on the calculator. It's only 2 problems in the homework, so it isn't a huge thing, but I'll put a video here that walks through how to do this. So to make the left sum program, what you do is you go to the program button, and then you probably wouldn't have a bunch of programs in there, so it might be pretty blank, but we just go from here and we go over to new. We're going to make a new program. So you hit enter and create new. And now this blinking A just means it's in alpha lock mode, which means that these letters on the upper right side of each key, those are going to show. So I'm just going to call this left sum. So I will go, actually I think I already have one in there called left sum, so I'm going to call mine L sum instead. So you just go through here and look for the letters you need to type up the name. Okay, so I'm going to call this L sum, and then once you get your name in there, just hit enter. And then what we want to do is, when we run the program, we want it to clear the home screen. Okay, so to get to that, we want to go to program again, press program, and we want to go to the input output. Okay, there's control input output. Go to input output and just go down until we get to clear home, which is right there. So hit clear home. So it'll clear the home screen, and then just press enter. And then we want to store 0 in our sum. So I press 0 and then press stores in. So stores in, and then I want to call it S. So to get to the S, press the alpha key. And then once the alpha key is pressed, then we can press the natural to get that S. Okay, so hit enter on that one. And then we need to input the minimum and the maximum. So we go to the program again. And this time we go over to input, output again. So go to input, output, and we want to input. And then what we want to do is put a parenthesis, put a quote, and then whatever follows the quote, it will display on the screen for the user when the program is run. So the easiest way to do this is go to second alpha, which will put it in alpha lock mode. So go second alpha, and then if you go over to, let's see, where does it go? Right here above the plus is this little quote to the right, so press this, and then I'm just going to press X, and let's see, does this, yep, you can still use that X even in alpha. And then I need to put a little blank just to make it easier to read for the whoever's running the program, for the user. And see above the 0, just to write a catalog, there's that little, it's trying to show a blank space. So press that and it'll just move the cursor over. And then we need to type min for the minimum. So I just type MIN. Then I want to leave a little space again, so it'll be neat when you're running the program, it'll be easier to use. And then I close the quote. So it's going to display that. So I need to get out of alpha mode. So I'm going to press alpha. And then we want to press a comma. And then we want to tell it where to store this. So the user is going to input a number, the minimum, and we want to store it. So I go to alpha to get into alpha mode, and then I'm going to store this in A. Right, that's the low point, so we need an A and a B. So I hit enter. We're going to repeat the same thing to find the maximum value. So you go program, go to input output, select input. Then we do the same thing, but I want to say X max. So I'm going to go second alpha lock, and then put the quote here. Go X space, and just type max, MAX, and another space, Now the nice thing is I'm going fast, but you can always press pause. So it's actually a little quicker. In the classroom, it's a little slower to do it this way. Let's see, so then I need the alpha, or I need the quote again, quote, and then get out of alpha lock mode, hit the comma key, and I want to store this one in B, so I go alpha B, enter. Okay, so now I've got the low, you got the high, now we need to know how many rectangles, so go to input again, so you go to program, input, select input one more time, and this is the n, how many rectangles do we want, so I'm just going to go, this time I'm just going to go alpha, quote, alpha n, alpha space, I guess I could have put in alpha lock also, but we're almost done with this part, alpha, the quote, and then we go comma, alpha n, so it's going to ask the user how many rectangles, and it's going to store that answer in the variable n. Okay, then we need to set up our delta x, so I'm going to go b minus a, so I go alpha b minus alpha a. We're going to divide that by n, divide that by how many rectangles it wants, so you go alpha n, and we're going to store this, in alpha d, so that's like our delta x. Okay, then we start our for loop. So for the for loop, we go back to program, and this is a control, so go down here to number 4. Thinks that's a coincidence, number 4 for the for loop. So go 4, and then we need our index or our counter. Typically we just use I, so I'll just use I. And we go comma 1, comma alpha n, for I equals 1 to n. Then it's going to repeat whatever it sees until it sees an end. So we're going to go alpha s plus. Okay, now we need to get a value from our function that will be stored in y1. So to get to y1, we go to this variables button. We go to vars, go over to y variables, and we're in function mode, so just hit enter for that. And there's y1, which is what we want. So I select that. And then I put in here a, our minimum value. So I go alpha a, close that. And I'm going to store this in the sum, alpha s. Okay, so it's going to store that in s. And now we want to advance to the next rectangle, so we go alpha a plus delta x, which is in D, right? We're going to store this in A. Okay, and then we can end the for loop, so we go program, and number 7 is end. And then we display our answer. So to display, we go to program, input, output, go to display, and then we hit D times S, so we go alpha D times alpha S, and that's the end of the program. So to get out of the program, you just go second quit. And now just to try it out on the rectangle problem, I'm going to go to y equals and type x squared. Okay, and then go second quit. And to run the program, you just go to program, and it's on execute. So I go down, have to find mine, there it is, left sum. And I just hit enter. And the minimum, if we just try one out, I'm going to go from 0 to 1. If you go, n is 4 rectangles, we get 0.21875. So hopefully that worked out. Like I said, it's not a huge deal if you don't program that in, but there's a couple homework problems. It makes it a little easier if you have it. All right, one last problem we should look at. This is one that's like some in the homework. You have number 17 and number 19 in the homework. And they say this, they say use definition 2 to find an expression for the area under the graph of f as a limit. Do not evaluate the limit. They don't really have to say that do not evaluate the limit part. That's just, these limits would be quite a handful. But they just want us to get it set up. So it talks about definition 2. Okay, this is on page 377 in the 9th edition. It's also on page 371 in the 8th edition. And then it's, if you use definition 2 with sigma notation, which makes it much easier. Sigma notation, that is on page 378, right on the very next page with the 9th edition, and page 372 with the 8th edition. Okay, but basically what it says is this. So what all of this says is the area equals the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I delta x. And we'll have all kinds of fun evaluating these in the next section. Now note this is using right endpoints because look, it says f of x sub I and I starts from 1, not from 0. So this is using right endpoints. Okay, just it doesn't really matter. It's just something to note. It's not starting at x sub 0, it's starting at x sub 1, so we're using right endpoints. Okay, so to do this problem with this definition, we look at what they're saying here. X is between 4 and 7, so this would be like our A and B. So we can go ahead and figure out delta x. So delta x is going to be 7 minus 4 over n, which is going to be 3 over n. And we know we're starting at 4, so x sub 0 would be 4. And then x sub 1, well, that's going to be 4 plus delta x, right? So that's going to be 4 plus 3 over n. You can think of how we develop this just in class, and you'll see it coming through here, how we made the rectangles, right? So we start at x sub 0, then we have x sub 1. If we look at, like, say, x sub 2 is going to be 4 plus 2 delta x's, right? We go over 2 delta x's to get to that one. So that's going to be 4 plus 2 times 3 over n. And if you just think like generally x sub I, that's going to be 4 plus I times delta x, which is equal to 4 plus 3I over n. And that's what we need. Right, so if you look in this formula, we need x sub I, we've got that. So we basically have to figure out f of x sub I. So here's f of x, right? This is f of x right here. So f of x sub I just means wherever we see an x, right? Wherever we see these x's, we're going to put x sub I, which is this thing. Okay, so what we would get here would look like this. We'd say the area equals the limit as n approaches infinity. I'm just going to use this formula right here, but we know what f of x sub I is. So we have the limit of the sum I equals 1 to n. And then it gets a little messy, but this is x squared, so I need f of x sub I. So for x, wherever I see an x, I need to plug this in. So we're going to get 4 plus 3I over n squared. plus, now I'm over here, right? I'm right here. I just swap out the x with x sub I. So we're going to have, let's see, 1 plus 2x, but x is going to be x sub I, 4 plus 3I over n. And this is under the radical. Okay, so this part right here, that's f of x sub I, and then times delta x. Delta x is 3 over n. So we go times 3 over n. And that is what they are looking for. That is the expression for the area under the graph as a limit. It's a limit of Riemann sums. These limits are quite a handful. Even the easiest ones are a handful, as we'll see. But we won't have to do these limits for long because the fundamental theorem of calculus is going to come to our aid, thankfully. Okay, so that should get you started. There's went over quite a bit. It's a sort of a tedious section. But go ahead and give it a shot. And if you have any questions, let me know.